Awesome. Hello, guys. Welcome to part 3 of my STEAM project video. This part is going to be on velocity, acceleration, and displacement and their derivative applications. So let's get started. Awesome. So this is going to be a little bit of a shorter video, but let's work through it. So part 3, application derivative laws. Derivative laws can be applied to the real world through relationships between displacement, velocity, and acceleration. Their relationship is connected through the derivative laws in the following manner. So let's get a new color. Let's go purple. Awesome. So as we can see here, the statement let t equal time. So we know that t in these equations is time. S of t is equal to displacement over time. I always wondered why it was s. Anyways, why is that not just d? V of t is equal to velocity versus time, and a of t is equal to acceleration versus time. So now that we know that, we can see the relationship between the three is that velocity is the first derivative equal to the first derivative of displacement. So if a person's walking that far and they walk 8 meters, let's say, taking the derivative of that function, whatever the function may be, will give you velocity, how fast they were walking. And going over to the second relationship, we have a of t, so the acceleration function, is given by either, so there's two possibilities to get to this one. You can take the second derivative of the displacement function, so take the derivative of the 8 meters walking plus the derivative again, or you can just take the first derivative of the velocity function, which is what we have right here. Either way, you still get to the acceleration function, no matter which or how many derivatives you take. Using the above information, we can answer questions related to 2D straight line problems involving displacement, velocity, and acceleration. Let's get into it. Highlighter, freehand. Let's go blue. All right, so example 3. A particle is moving along a straight line path. So it gets a little bit more complicated if you are dealing with non-straight, non-linear paths in terms of acceleration, velocity, and displacement, because instead of going from point A to point B, you might instead of going that's a straight line relatively, you might go, maybe take a stop here, go here, do a little circle, and then finally get to point B, right? So there's a little discrepancy between the two, and that's why we're only dealing with straight line problems for now. So it is modeled by the equation S of t is equal to that function right there, where t is equal to the time in seconds and s is the displacement of the particle. That should be S of t. S of t is the displacement of the particle in meters. Determine the velocity and acceleration of the particle at 4 seconds. Wonderful. Okay, so what we have to do basically is we're given the displacement function. As we can see right here, S is the displacement of the particle. Oof, that is rough. But displacement of the particle versus the time, t. And if you recall right here, we see that the first derivative of the displacement function is equal to velocity. So let's go ahead and do that right now. You see we have the same sort of relationship marked right here. So the velocity function is equal to the first derivative of the displacement function, and we do that right here. So bring the 2 down. This is again power law. 2 times 4 is 8. 2 subtract 1 is 1, so you don't have to put it. And then again, you got to bring the 1 down. 1 times 5 is 5. 1 subtract 1 is 0, so no need to write the t. And this is the derivative of the v of t function. But we are not done, or the derivative of the displacement function, and it is the v of t function, but we're not done here. We have to find when the velocity is, what the velocity is at 4 seconds. So simply just add or insert 4 into this equation, as you can see right here, and we end up with 37. So If you guys haven't taken physics before, we know that this is really 37 meters per second, or whatever the measurements might be. In this case, it is meters per second. That's a rough M, but we'll gloss over that. Moving on to acceleration, we have, let's switch colors here and see if blue. Acceleration is equal to the first derivative of velocity, or, as you all know, the second derivative of displacement. So I'll run through both scenarios, even though we don't really need to. All right, so let's focus on this one. So the v prime of t, well, we have v of t right here, right? So let's take the derivative of this. So we have a 1 right here, imaginary little 1, multiplied by 8. 8 times 1 is 8. 1 subtract 1 is 0. No need to write the t. And plus 5, again, if you remember back to part 1 of this, 5s and any constant, not just 5s, any constant value will not be factored into the derivative, so we can leave it as blank, and we have the acceleration at any point is equal to 8. Now, this might trip some people up right here, because you might say, hey, there's no t value. Where do I insert the 4? This, honestly, all this means is that the acceleration is constant. So no matter at what points this particle is moving, it's always accelerating at the same velocity, or at the same speed. So there's no change, there's no up, there's no down, it's all straight. And again, if you've worked in physics, we know that acceleration is denoted by meters per second squared. Oof, that is so much better than that one. Wow, getting good at this. Anyways, yeah, that's it for this question. So pretty simple. Again, it's just applying the derivative knowledge that we've learned back in part 1 and 2 to a little bit of a word problem. Part 4, it'll get a little bit more complicated, but stay tuned. Thank you guys for watching. Oh, stop share. Thank you guys for watching. Hope to see you part 4. Bye now.